Okay, cool. So, hello everyone. I welcome you all. So, the agenda for today's session is Introduction to Dynamic Programming, right? I hope that you guys are well, and I hope that in today's session, all those people who are beginning their journey with dynamic programming or have a slight idea about how dynamic programming goes, or maybe you have some intermediate idea about how dynamic programming works, for all these people, you get to know something new. This is the main agenda that we are going to follow, right? This will be an introductory session on dynamic programming, where we will be focusing on the root concepts that will be acting as the building blocks for tougher dynamic programming problems that you are going to face later, right? So there's a very famous quote. I guess everyone would have already heard about it. That those who don't remember their past are condemned to repeat it, right? We will see what exactly this phrase signifies, and we will see that how you guys can use dynamic programming in your competitive programming contests and data structure and algorithmic problems. So without any further delay, let's just take a deep dive and try to master the concept of dynamic programming, right? Okay. If I'm audible to everyone, just quickly drop a yes or no in the YouTube chat section. And if you will be having any doubts, guys, in the live session, just make sure that you are dropping your comments in the chat section. I'll be seeing them live and taking all of your doubts. So just quickly ping a yes or no if I'm audible, and then maybe we can just quickly start, right? Okay. So for all those people who don't know about me, or they have just uh, came to the channel of CodeChef. So I'm Sanket Singh, currently working as a software development engineer at LinkedIn. Previously, I worked as a software developer at InterviewBit as well as a product engineer at Coding Blocks. In 2019, I cracked the Google Summer of Code under Berkman Klein Center at Harvard University, where I worked with a Meteor.js based project under Harvard University. Previously, I've also worked as a former research intern at Indian Space Research Organization, the Ahmedabad Bhopal Center in Gujarat. Till now, I have taught more than 7,500 programmers in data structures, algorithms, competitive programming, and fundamentals of computer science. I've worked with startups like Capture Fashions, Talview, Fable HQ, etc. Got rank one in few of the CodeChef long challenges, as well as won the Infosys Digital Megathon. So without any further delay, right? Without any further delay, let's just start and see what's the agenda for today is. So we'll take a motivation problem. We'll take a motivation problem, and we will see that how we can apply dynamic programming there, right? We will take an introduction on how dynamic programming works. We will see a bit about what are recurrence relation and why they are exactly required to build. We'll see the concept of mutual exclusiveness and exhaustiveness in very depth. We will see what are the state of a problem. We will see what is memoization and tabulation. And obviously, considering the fact that this is a competitive programming session, we will be doing a lot of problem solving, right? Okay. Okay, next time I'm from GJS IPO New Delhi. Cool. Okay. So let's just start, guys. Let's just start. If everyone is able to see the text editor, uh, just drop a yes or no. Just quickly drop a yes or no, guys, if you are able to see the text editor. Okay, cool. Let's just start. So before moving forward, that why do we need dynamic programming and what is it? So let's just take a small motivation problem, right? Let's just take a small motivation problem. So I read this on internet. So I was exploring the fact that how somebody can explain dynamic programming easily to a 5 or 6-year-old kid, right? So I guess a lot of you guys might have already read about this approach. So let's say that there is a child, right? And he is learning how to count, right? So if you will just draw 4 ones in front of it, so what he or she will do, she will just count one by one that this is 1, 2, 3, and 4. So there are total 4 ones that have been drawn in front of him or her, right? Okay. Now let's say if you draw one more line and ask them that now what's the count of lines here? So if they have already taken the count that, okay, there were already 4 sticks or 4 lines present on the screen, and somebody has drawn one more. So what's the new value? It is 4 plus 1, right? If I will draw one more line, they will automatically say that, okay, we have already counted till here. So the new value is 5 plus 1 equals to 6, right? So this is the basic gist of dynamic programming. Anything, anything that you have already done, anything that you have already computed, any value that is already available to you, or you can make sure that this value can be available to me for the very next time. In that approaches, in that problems, you can apply dynamic programming, right? So what happens in the case of dynamic programming is, if at any point of time you have a problem that can be further divided into smaller subproblems, and the smaller problems repeat themselves, then we can get an intuition of DP. Then we can get an intuition of DP. Does that make sense? Are you guys able to understand the basic gist of what is dynamic programming and why exactly it is required? Because let's say if someone asks the same kid that, okay, now if I draw one more stick in front of you, so if he or she will go and count them once again, all over again, then it would be a very hectic task for them to do, right? Instead, they can just memorize the fact that, okay, last time it was 6, somebody has added one more. Obviously, this is going to be 6 plus 7, right? Does that make sense? Next time, bro, we will discuss about it. We can discuss about it. If you can just stick to the session for the very last, we can discuss your doubts at the very last. Don't worry. I can give you some insights over that. Or maybe you can connect with me on LinkedIn. I can take your doubts there. Right? Okay. So let's just take a problem. Let's just take a problem. Right? Okay. So how many of you guys are aware about the basic Fibonacci series? Don't worry. We'll start with the basic stuff. Then we will try to increase the level one by one. I need to discuss a lot of concepts that would be easily understandable if you will take a very small and very easy problem to handle. How many of you guys already know that what is a Fibonacci series? Say yes or no. Okay, cool. So the Fibonacci series looks something like this. That is 0, 1, 1, 2, 3, 5, 8, so on and so on. Right? Okay. Now, if you are going to iteratively solve the problem that given a number n, you need to print the nth Fibonacci, considering the fact that the 0th Fibonacci is 0 and the first Fibonacci is 1, right? Then what you are going to do? You are going to start from I equals to 2. You're going to start from I equals to 2. And every time, you're just going to add the previous 2 Fibonacci's. Does that make sense? Does that make sense to everyone? Okay, cool. Now, let's just try to solve this problem recursively. How many of you guys have a basic understanding about what is recursion? How many of you guys know that what is recursion? Just drop a comment, guys, that you guys aware about what is recursion? Cool. So what can happen? Okay, so if you have a basic understanding, then that will be sufficient. If you are like very beginner and don't know a lot about recursion, then I would prefer you guys that I'll be taking a session on recursion this Saturday, so you guys can join that. That will be starting from very basic, just like the dynamic programming session that we are having. It is going to start from the very basic, right? Okay. So what happens with the case of recursion is, in the case of recursion, if we are going to solve the problem of Fibonacci using recursion, then what we are trying to say is that if we want to calculate the nth Fibonacci, right? So how about the fact that anyhow, any cost, you don't know how, but anyhow, someone gives you the value of the n minus 1th Fibonacci. Somebody gives you the value of n minus 1th Fibonacci and gives you the value of n minus 2th Fibonacci. Anyhow, any cost, right? So let's say you want to calculate the 5th Fibonacci. and somebody gave you what is the value of the third Fibonacci and the fourth Fibonacci, then can you guys calculate the value of the nth Fibonacci if you have these two values? Say yes or no. Let's say that this fib is a function that returns the nth Fibonacci, right? So let's say that if there is a fib of n minus 1, then it will be returning you the n minus 1th Fibonacci. N minus 2 will be returning you the n minus 2th Fibonacci. So if anyhow, any cost you have the both of the values, then cannot you just add both of these values and calculate the nth Fibonacci? Say yes or no. Does that make sense? This is the recurrence relation for Fibonacci. We will discuss few more problems that will be having some more recurrence relations. So just stay tuned. Don't worry on that part. Right. Recurrence relation for Fibonacci. So how we can simply define recurrence relation is, recurrence relation are the mathematical representations that will be combining different states of the function to calculate the corresponding answer recursively, right? So you can say that it's the mathematical representation of the recursive function that we are going to implement. Does that make sense? Simply, what is recurrence relation? You can say that it's the mathematical representation of the recursion logic that you guys are going to implement. Does that make sense, everyone? Guys, does that make sense? Right? Okay. So if someone will ask you what are recurrence relation, just simply give them the definition that in simple words, in layman terms, you can define recurrence relation as the mathematical representation of the recursive logic for the problem under the observation. Right? Okay. Now let's just visualize this recurrence relation. So if let's say you want to calculate fib of 5, right? Okay. If you want to calculate fib of 5, you need the value of fib of 4 and fib of 3. If you have the value of fib of 4 and if you have the value of fib of 3, then can you calculate fib of 4 using fib of 3 and fib of 2, and similarly fib of 3 with fib of 2 and fib of 1? Does that make sense? Fib of 3 with fib of 2, fib of 1, fib of 2 with fib of 1, fib of 0. And here also you will be having f of 1, f of 0. Similarly here, f of 1, f of 0. How many of you guys are able to understand this binary tree? How I draw this binary tree, right? So here you can see that every time when you are going to calculate fib of 5, you need two values, fib of 4 and fib of 3, right? Then you don't have the value of fib of 4, then you will go and calculate the value of fib of 4. This is fib of 3 and fib of 2. Then currently you don't have the value of fib of 2 and you don't have the value of fib of 3. You are going to calculate f of 2 and f of 1, so on and so forth. Now there is an MCQ for you guys. What kind of traversal a recursion shows? Is it a BFS? Is it a DFS? Or is it a level order traversal? You guys tell me. Is it a breadth first search? Or is it a depth first search or depth first traversal? Or it's a level order traversal? What do you think? Recursion is what? Okay, few people are answering. Everyone, try to answer. What kind of traversal? It's a depth first search. It's a depth first search. Why it's a depth first search? Because here you can see that you were not having the value of fib of 4 and a fib of 3, right? So you first went to the very depth of fib of 4's subtree to calculate the value of fib of 4. You have left behind fib of 3 for some period of time. Then You came to fib of 3 and fib of 2. You don't have the value of both of them. Then you go and calculate the fib of 3 using the subtree rooted at fib of 3, right? So you have left behind fib of 2 for some time. Then you came to fib of 2, then you came to fib of 1, and this is the base case. Does that make sense? So whatever subtree you are going to traverse, you're going to go to the very depth of the subtree in order to calculate your answer. So the first and the foremost thing that we can say for sure is the recursive logic seems to be like a depth first search. Does that make sense to everyone? Does that make sense? Right. Okay. Now, here you can see that this subtree rooted at fib of 3 is also present here. Can I say that this subtree which is rooted at fib of 3 is same to same present here, right? Okay. This subtree of f of 2 is same to same present here and present here, right? So what we can say is that if you have a problem in your hand, fib of n, you need to calculate fib of n, and for all k where k is less than n, right, then fib of k is a smaller subproblem. Can we say that? For all the values of k where k is less than n, it will act as a smaller subproblems. And if it shows the property of overlapping or repeating subproblem, then what we can say is that there is some task that is going to be executed again and again and again, right? There is some task that is going to be executed more than once, right? Because we calculate fib of 3 here, then we again calculate fib of 3 here. So the whole time that we need to calculate fib of 3 is going to be repeated again. Does that make sense? So anyone who can tell me what is the time complexity of this recursive solution? Anyone who can tell me the time complexity of this recursive solution? Cool. Exponential, right? Why exponential? Because every time you are going to make 2 calls, right? At every level, for each node, you will make 2 calls. So, and here you can see that the maximum depth that you have is going to be equal to n. So in the worst case, it will be something like big O of 2 raised to the power n. And that is going to be very huge. Okay. Now, how about the fact that, let's say, we play a bit smart. I know a lot of people might be feeling that, okay, this is trivial dynamic programming, but we need to have a subtle base to introduce a harder level problem. So just bear with that, right? Okay. So now what we can say is that we once got a chance to get the value of fib of 3, right? We once got a chance for the very first time to get a value of fib of 3. How about the fact that we memorize it? That, okay, if at any point of time, right, there is any sub problem that is going to be computed for the very first time, and we have an intuition that sub problems are getting repeated in this Fibonacci series, maybe we can memorize them, right? And if we are able to memorize them, then if they are going to be called again for computation, we can just return from this memory. We can just directly return from this memory. Does that make sense? It's simply like a caching mechanism, right? It's simply like a caching mechanism where you will cache the data for some time, considering the fact that this data might be required again, right? So you can use this caching mechanism. Okay. And let's say if you use the caching mechanism, so how things will go on? You will be calculating f of 5. It will be calculating f of 4 and f of 3. You don't know f of 3. Neither you know f of 4, but this is a depth first search. You will first go to f of 4. It will go to calculate f of 3, f of 2. Then it will go to calculate f of 2, f of 1, and it will go to calculate f of 1, f of 0. These are the base cases. The answer you already know. Okay. Now, this will return, this will return. You have a chance to store f of 2. We will store it, right? And return its value. Then f of 3 will go. It's a base case. It will return the value to f of 3. You have a chance to store f of 3. We will store it. How? We will see. That's like a basic programming problem. Don't worry. Now we came to f of 4, returning the value of f of 3, and f of 3, f of 4 called f of 2. Now f of 2 was already stored. F of 2 was already stored. So don't you think we can just directly return the value from the store? Does that make sense? Right. Then f of 4 is computed for the very first time. Let's store it. Return its value to f of 5, and f of 5 calls for f of 3, and f of 3 has been already stored. Bingo. This has been already stored. You can directly return it from the store. And here you can see that. Here you can see that if you will visualize the tree carefully, then this is like a skewed tree. Can we say that? It's a skewed binary tree kind of. Right? And in a skewed binary tree, we have the nodes of order of n. Right? And here you can see that we are just going to the depth of n, and rest every time we are just using a constant time operation to return the value from the store. So we have reduced the complexity from 2 raised to the power n to n. Does that make sense? Guys, just say yes or no. Are you guys able to understand that a huge amount of time is getting saved here? Guys, are you able to understand the problem? Okay. So let's just take one more problem. Let's just take one more problem. And you guys will tell me the recurrence relation for that. So let's say there are n friends who want to go to a party, right? And considering the fact that this is the COVID situation, so after everything becomes normal, we will definitely go and party. So there are n friends who are planning to go to a party, right? Now, there is a constraint that one guy can one guy or a girl can either go alone or they can go in a pair, right? What you're supposed to do, you need to calculate the number of ways they can go to party. Does that make sense? So let's just take an example. Let's say there are 3 friends, A, B, C, right? Okay. So in how many ways these 3 friends can go to a party? One way can be all of them go alone. All of them are going to go alone. Or AB makes a pair and C goes alone. Goes alone, BC makes a pair, AC makes a pair, and B goes alone. So there are 4 ways when you have 3 friends. Does that make sense? You guys will tell me the recurrence for this. And from this problem, we will try to introduce the concept of mutual exhaustiveness and exclusiveness. No web hub. There will be a slight change. Guys, think about it. Think about it. How you can write a recurrence relation. We will solve some basic problems from maybe ArtCoder, and I'll give you a homework problem as well. That would be a bit hard, I know, but let's see. anyone with any idea that how you guys can write a recurrence? Can anyone tell me if I have two friends, in how many ways these two friends can go? Can you answer this? Kaustubh says 3. Anyone else? Okay. If you have two friends, let's say A, B, there is one way both can go alone or both can go together. Two ways. Does that make sense? Okay. Shall we start? Shall we start writing the recurrence? Guys, quickly ping me a yes or no that if we can start writing the recurrence. So what will be the recurrence, Amit? If you one step include, one step exclude, then what will be the recurrence, exact recurrence? Okay, sure, cool. Guys, listen to me very, very carefully. If you have any thoughts in your mind for some time, keep them aside. Listen to me very, very carefully. Most of the time, the logic will be understandable in one go, or maybe one more iteration. But this is very, very easy, like very easy kind of a problem. Okay. So let's say you had n frames, right? Let's say you had n frames. Okay. Now let's just make a choice for the nth friend. We will try to find the element of choice. What is the element of choice? What is the element of choice that at my current problem or my current sub problem, what is the choice I have to make? Right? That's called as the element of choice. Does that make sense? Collect what will be the recurrence? Maybe you can write in the chat section. Right? Okay. So let's just make a choice for the nth friend. The one who is the last one. Let's just try to make a choice for him. Okay. So we will define a function f n where f is a function that returns the number of ways, right? Okay. Now f of n will return that considering all n friends, that we have all the n friends, in how many ways they can go. Okay. So let's say the last one, the nth friend, he goes alone, he or she goes alone. Then how many friends are left? Nishant, you are on the right track, I would say. Just small correction is required in your recurrence. Guys, tell me, if the nth friend makes a choice to go alone, he or she makes a choice to go alone, how many friends are left for which we need to make the choices? For example, if you are not able to understand, for example, let's say there were 3 friends, A, B, C. C is the last one, right? C says, I will go alone, right? So f of 3 represents the total number of ways in which all 3 of them can go, right? If C had made his or her choice, then how many of them are left to make a choice? 2. So we can say f of n minus 1, that is the number of ways in which n minus 1 friends can go, either by making a pair or by going alone, right? They will contribute to the answer. Why? Let's see. So C says, I will go alone. So in how many ways AB can go? A and B both can go alone, and AB can go in a pair. In both of these ways, C is going to go alone. So here you can see we got the 2 ways. From the total 4 ways, we got the 2 ways. Does that make sense? Are you able to get this logic of f of n minus 1? Quickly ping a yes or no in the chat section, guys. Quickly spam the chat section that if you are able to understand that why this f of n minus 1 is coming. Okay. So Himang says no. Okay. So Himang, let's say you had f of 3. F of 3 says what? Number of ways in which 3 friends can party. Right? Okay. Now, if the last friend says, no matter what, I will go alone. So one friend had made his or her choice. You can't do anything about it. How many friends are left for which you need to make a choice? Hima, tell me. There are 2 friends left, right? So can you say that the answer of f of 3 will depend on the answer of f of 2? Why? Because in all the ways, these 2 friends can go to party, which is both can go alone or they can make a pair. In both of these ways, C is going to go alone, right? So we got 2 ways. Does that make sense? So f of 2 will contribute something to f of 3 because the element of choice of the third friend has been taken that he or she wants to go alone, no matter what, right? Okay. Now this was for going alone. Now the nth friend had a choice that, okay, this time he says, no, I don't want to go alone. I will make a pair. Yes or no? He had a choice, right? He or she had a choice that now I'll make a pair. I don't want to go alone. What will be the number of friends for which you need to make a pair? You need to make the choices. You had n friends. Nth friend now says he or she wants a pair. Right? He or she wants a pair. So if he or she has decided, then how many friends are left for which you need to make the decision? Say yes or no. Sorry, write the answer. Can I say it will be equal to k into f of n minus 2, where k is the number of ways the nth friend can make a pair. Yes or no? The number of ways in which the nth friend can make a pair multiplied by f of n minus 2. Why? Let's just see. So let's say you had 4 friends A, B, C, D. You had 4 friends A, B, C, D. D is the nth friend. Right? Okay. Now let's say D says I want to make a pair. No matter what, I want to make a pair. Okay. So D can make a pair. But D can make a pair with whom? D can make a pair with A. D can make a pair with B. D can make a pair with C. He or she has 3 choices. Okay. Let's say D makes a pair with A. Then D makes a pair with B. D makes a pair with C. Okay. So how many friends are left? If D makes a pair with A, B and C are left. If D makes a pair with B, A and C are left. If D makes a pair with C, A and B are left. So in the number of ways BC can go, D will go with a pair as A. So how many ways BC can go? BC can go alone, or they can also go in a pair with DA as a pair. Then here A and C can go alone, or DB as a pair and AC as a pair. Similarly, A and B alone, AB as a pair, DC as a pair. Does that make sense? So can you see that K, if K denotes the number of ways to choose partner, which was equal to 3 here, multiplied by f of n minus 2, will give you the number of ways the nth friend can make a pair. Does that make sense? So can I write it? K of f of n minus 2, k into f of n minus 2. Everyone, just quickly spam a yes or no if you are able to understand this. Guys, say yes or no if you are able to understand this. We will define what is the value of k. We will check what is the value of k. But is this understood to everyone? Okay, Devansh, एक बारी मैं दोबारा repeat करूँगा. Don't worry. Okay. What is the value of this k? What is the value of this k? When you had 4 friends, A, B, C, D, you were making a choice for D. D can make a pair with either A or B or C. So 3 choices. Let's say you have A, B, C, D, E. If you are making a choice for E, E had a choice that he or she can make a pair with A or B or C or D. So 4. So let's say you have F1, F2, F3, Fn, total n friends. So this f of nth friend had a choice to make a pair from n minus 1 people. So can I say k is equals to n minus 1? So can I write n minus 1 multiplied of f of n minus 2? And this is for making a pair, right? So one sub problem was what? That nth friend can go alone. So how many ways rest of them can go? F of n minus 1. And in front of every every those ways, we can just append directly the nth friend. The other sub problem was what? That he or she wants to make a pair. So the number of ways in which he or she can make a pair multiplied by what is the ways for the rest of the people to go. Now, can I add the answer from both of these sub problems to get the answer of f of n? How many of you guys agree with this? How many of you guys agree? Quickly just drop a yes or no. Right? Okay, cool. One last quick iteration. Right? A, B, C, D, f of n. You are going to make the element of choice for f of d. If f of d is going to go alone, then how many friends are left? In all the ways A, B, C can go, f of n minus 1 plus. Now D wants to make a pair. If D makes a pair with A, how many people are left? F of n minus 2. Now, if let's say D makes a pair with B, how many people are left? 2. That is f of n minus 2. If D makes a pair with C, how many people are left? F of n minus 2. Can I say this is equivalent to f of n minus 1 plus 3 into f of n minus 2, or instead of this 3, I should write n minus 1, which is equals to f of n. This is the recurrence relation for the problem, right? Devansh, are you able to understand this now? That how I came up with the recurrence relation? Guys, just drop a yes or no if things are understood till now. Everyone. Okay. Now, let's just introduce the concept of mutual exclusiveness. What is mutual exclusiveness? Let's just talk in simple terms. Let me ask you a question instead. Do you think there is any way, which is coming common from this part or this part? That is, do you think there is any permutation of your friends to go to a party that is getting calculated twice? That is coming from here as well and here as well, and we are adding it twice. No, instead, let's say you had ABC, right? If C says he wants to go alone, then AB alone, C alone, AB pair, C alone. These two are coming from f of n minus 1. How many of you guys agree with this on me? Okay. If C says he wants to make a pair, then AC a pair, B goes alone, AB a pair, sorry, BC a pair, A goes alone. Two ways coming from here, and this is coming from f of n minus 2 into n minus 1. This part of the subproblem, this part of the subproblem. Do you think there is anything common or anything repeated that we are calculating? Okay, that this method is calculated once here and let's say once here as well. Is there any way that is getting calculated again and again? Don't look at the term. I'm asking that, is there any permutation which should be counted once, but we are counting it twice or more? Is there any way? Is there any way, right? A alone, B alone, C alone. Do you have any permutation like this inside the second set? Let's say this is a set B, this is a set A. Do you have any permutation like this in set B? Say yes or no. Any permutation where A goes alone, B goes alone, C goes alone. This way of friends going to the party, there is no such permutation? Okay. Is there any permutation AB goes in a pair, C goes alone in the set B? Is there any permutation like this? Is there any common permutation like this? Say yes or no. AB goes in a pair, C goes alone. Is this thing present inside the set B as well? Or is it just present inside the set A? No, right? So can we say that the ways which the set A is calculating are all unique, and the ways which set B is calculating are all unique? Does that make sense? Both of them are calculating unique ways. We are not adding any way twice, which would lead to a wrong answer. Does that make sense? This is the property of mutual exclusion. This is the property of mutual exclusion, that there is no common answer coming from both of these subproblems. There is no such common answer which should not be counted twice, thrice, or more. Right? There is no such common problem. Right? I was not asking about recomputation of a subproblem. I was asking that, is there any permutation that will be coming finally that is recomputed again? No. So this is mutual exclusiveness, that whatever recurrence you are building, it should follow mutual exclusiveness with the subproblems. That is, whatever your subproblems are giving, the answers that your subproblems are giving should be unique. And if two of your subproblems have common answers, or they have some common subproblems that are coming from them, right, then you should remove the common ones. So here we didn't have any common subproblems, so we don't need to remove anything. Does that make sense? Also, what is mutual exhaustiveness? Do you think by using this recurrence, is there any way such that n friends go to a party and that way we won't be able to calculate? That is, our answer is going to be less than what is supposed to be. Is there any way that we will be losing any answer? Like, let's say this one, we are not able to calculate it, right? Any valid answer, we are not able to calculate. Do you think there would be any such case? Say yes or no. This is the concept of mutual exhaustiveness. That is, whatever recurrence you should be writing, it should calculate all the possible unique answers, right? There should not be any unique answer that is not handled by your recurrence. In that case, your recurrence will be invalid. Are these two properties understood by you guys? That these two properties are important for your recurrence to be valid. So I'll be dropping a question. It's a bit hard one, right? Trust me, it's a bit hard one. I want you guys to try it, right? Maybe in any other free special class, I would take it, right? Try to build recurrence relation for this problem. Try to build a recurrence relation for this problem. It is pretty hard, trust me. It's not that exactly trivial. It's like medium kind of, right? Okay. So try to build a recurrence relation for this problem. You will be able to see that there are some common sub problems coming from your recurrence and you need to remove them, right? Yes, and for every valid recurrence, both mutual exclusion and mutual exhaustiveness should be satisfied. Ashutosh, I would say for cross-checking, you can take some cases, right? Because if you want to be following mutual exclusiveness, then you will be getting more answers than required. If you want to be following mutual exhaustiveness, then you will be getting less answers than required. So this can also be a marker for you to check. How many of you guys are able to understand this concept? Because recurrence relation is not directly a programming concept. It's like a mathematical concept, right? And we should follow the concept of exhaustiveness and exclusiveness in order to build a right recurrence relation. Does that make sense to everyone? Just quickly drop a yes or no so that we can proceed. Guys, can we proceed? Are you able to enjoy the lecture? Able to understand something new? Able to learn something new? Right? Okay, cool. So let's see what was the agenda. Okay. Now, let's just come back to that Fibonacci problem, right? So how to code a DP? Now we know that how to build recurrences. We know that how to build our recurrences. Now recurrences can lead to very large number of problems, sub problems that are also repetitive, right? Okay, I'll deal the concept that when a problem should be solved by DP, there are two properties. I'll come to that if anyone is waiting for that, right? Okay, so let's just see how we can code a DP. First, see how to write a recursive Fibonacci. So recursive Fibonacci is very easy. We will write int fib of n. If n is double equals to 0 or n double equal to 1, return n, right? And if this is not the case, then what we will do? We will do int answer is equals to fib of n minus 1 plus fib of n minus 2, return answer. This is the basic recursive code. Now what I said, if there is any sub problem that is getting computed for the very first time, let's store it. So let's just make an array, right? Let's just make or let's say a vector, right? Let's just make a vector DP of some size S. I will tell you what should be the size, and let's just initialize it by -1. I will tell you what will be the size. This is a very important concept. Okay. Now, what DP at I shows? DP at I represents the ith Fibonacci, right? And if DP at I is double equals to -1, it means we have never calculated ith Fibonacci. How many of you guys are able to understand this condition? Say yes or no. If this point is true, then at any point of time you can say if dp at I is not equal to -1, then you have already, sorry, dp at n is not equal to -1, then obviously for a smaller subproblem n dash, you have already calculated the Fibonacci. Directly return it. Return dp at n. Does that make sense? Vaibhav, we will be coming to that. We will be coming to that. Don't worry. And if this check is never executed, then obviously you have never calculated it. So what you are going to do? You will do dp at n. You have the answer with you is equals to answer. So this is the step to store it. This is the step to retrieve it. If you are able to build a recursive logic, 90% of the time, you will be able to submit it using a DP. Either it is a contest problem, either it is your interview problem, anywhere. Does that make sense? Right? Okay. Now, what should be the size of this DP? What should be the size of this DP? Size should be equal to number of unique states. Now, you guys will ask me, Sanket, what is a state? We have never discussed about any state inside the whole concept. So what I can say is that in easy terms, you can understand that state can be defined as a subproblem. A subproblem can be considered as a state, and the number of unique states represents the number of unique subproblems. And here you can see that if we know that how many number of unique states we have, then do we need a space more than that? No, we would be wasting that much amount of space, right? So what we can do, we can keep a fact that what is the number of states, unique states here. And if you will keep a track on the Fibonacci tree, what are the unique states of a Fibonacci tree? 1, 2, 3, 4, 5, 6. From 0 to 5, total 6 Fibonacci's can be there. So I can make a DP array of what size? N plus 1, if you want to calculate the nth Fibonacci. Does that make sense? So, Shrenu, what I'm trying to say is that you will be taking a vector. You will be checking the fact that if at any point of time you have already computed your Fibonacci or not. If yes, then return directly. No need to do any more computations. Otherwise, store it. Now, what should be the size of this DP array? The size of the DP array, maximum size that you should take for a subproblem, for a problem, is equal to the number of unique states. What is a state? State can be in easy terms defined as the number of unique subproblems. Does that make sense? Does that make sense? So fib of 5 will be depending on fib of 4 and 3, then 3, 2, then 2, 1, then 1, 0. So how many unique states are there? 1, 2, 3, 4, 5, 6. 6 unique states are there. Does that make sense? Now there is one more very important concept associated with a state. The number of parameters that your state depends on can give you a hint generally on the dimension of the DP storage. Right. So what I'm trying to say here is that, you know, f of n is equals to f of n minus 1. plus f of n minus 2, right? Okay. Now you can see the fact. You can see the fact. Kaustubh, I'll be coming to that point. Don't worry. As I said, a state is what? A unique subproblem. So can I say f of n minus 1 was a subproblem? Say yes or no. Was f of n minus 1 a subproblem? Right? Okay. And this subproblem is depending on how many parameters? One parameter. That is value of n minus 1. Or let's say this is depending on just one parameter n. So can you say that we would be requiring a 1D DP here? So in the most of the time, the number of parameters your state depends on will help you to get the dimension of the DP. Now, sometimes in competitive programming, what will happen is you will define the states in 3 or 4 variables, and you will get a MLE. What is an MLE? Memory limit exceeded. So this is a hint for you. This is not a problem. This is a hint for you that the 4 parameters using which you have defined your dynamic programming state, you can reduce them. So these 4 parameters, let's say X, Y, Z, A, these 4 parameters have some relation between them. They have some relation between them, and you guys can build a relation to reduce the number of parameters on which your DP state depends on. Does that make sense? Till now, anyone having any doubt, just ping a yes or no to the chat section. Are you guys able to understand? Is the concept looking good? Right? Concept is understandable? Guys, tell me. Shall we start coding it? Okay, cool. It will be a very easy code. I won't take a lot of time because we need to discuss some problems. So, fibdp.cpp. I won't be building the whole template. That would be a bit overwhelming. Or let's say just build. No worries. Right. Okay. So we'll be taking an int n, c in n. We'll write a function int fib. Right. We'll pass the variable n, and we will pass the vector of int and dp. Right. If n double equals to 0 or n double equal to 1, return n. Otherwise, int answer is equals to fib of n minus 1 comma dp plus fib of n minus 2 fib of n minus 2 comma dp. Return answer. Before returning it, this is the storage step. We will do dp at n is equals to answer. If we have already computed dp at n, which is not equal to minus 1, we will return it. Does that make sense to everyone? So what we'll do, we'll make a vector dp of size n plus 1 initialized by minus 1, and we'll do cout n comma dp. Make sense to everyone? Just quickly ping me a yes or no in the chat section. Guys, say yes or no. Anyone having any doubts in the coding part? Anyone having any doubts in the coding part? Right. So let's just start. Let me take my input file. This is the output file. And where is my input file? This is the input file. Just a second. Okay, sorry. Yeah. Okay, so let's just give some inputs. Let's just try to calculate the 5th Fibonacci. I hope this works. Let's just build it. Okay, Sogata says why we are taking n+1. Just 1 second, bro. I'll be explaining. Let me run it. Here you can see the fifth Fibonacci is coming as 5, right? So the code works fine. So why I took n+1 to calculate fib of n. How many unique states are there? Can you tell me? To calculate fib of n, how many unique states are there? For example, you have fib of 5. So to calculate fib of 5, you need what? Fib of 1, fib of 0, fib of 2, fib of 3, fib of 4, and then obviously you will get fib of 5. How many states are there? Unique states. Can I say 5 plus 1? So for n, can I say n plus 1? And I need to make a array of that size, right? So young hacker has a doubt. Please ask what doubt you are having. Kaustubh, Swagata, are you guys able to understand this? Okay. So this type of DP that we have written, in which we have a recursive logic, we have a recursive logic, and we used a storage to store the answers. This is called as memoization or top-down DP. And mind my words, this is not memorization. This is not memorization. This is memoization. Does it make sense? Okay. So Webber says that what if we have huge number of states? So generally, Webber, what you need to do, you need to do some space optimizations, right? Because if you will be having a large number of states, then generally recursive logics can give you memory limit exceeded, right? So there exists a counterpart for that. Also, if you have a large number of states, then for beginners, what I can suggest you is that try to visualize the fact that are there some states which don't even need it to be computed for your answers, right? They are relevant, but for your current answer, they don't need to be computed. In that case, you can keep a map with you, right? And map will only grow till the point that you have some set of states. Does that make sense? Generally, to avoid this MLE kind of a condition, we will be using a bottom-up approach. We'll be coming to that. In bottom-up approach, most of the time you can do a lot of space optimizations. Most of the time, as I said, because sometimes there are not in bottom-up. But I would say these are a bit intermediate level concepts. Let's just focus on what do we have in bottom-up DP. So top-down DP is simple. Simple recursive logic, storage, and above that, return of storage. Okay. Now inside bottom-up, this bottom-up approach is also called as tabulation. Bottom-up approach is also called as tabulation. So what can happen is, if you know the order in which the states are computed, then we can use this. So what does this say? This says that if you know the fact that what is the order in which your states are getting computed from the very first to the very last, then you can use this. Okay, what I mean by that? If I know the value of the 0th and the first Fibonacci, then I can build the second Fibonacci. If I know the value of the first and second Fibonacci, I can build the third Fibonacci. If I know the value of second and third Fibonacci, I can build the fourth Fibonacci. If I know the value of third and fourth Fibonacci, I can build the fifth Fibonacci. Can I say that? Say yes or no. In this way, we know the ordering in which Fibonacci is getting computed. Say yes or no. Similarly, let's say in that friends party problem, let's say you had 4 friends. A, B, C, D. If you know that in how many ways A can go, how many ways A can go? A can go in only one way. In how many ways A, B can go? They can go in two ways. Now, to calculate the number of ways in which A, B, C can go, you just need the values of A and B, and we know the order that we should first compute A, then compute B, then only we should compute C. If we are able to decipher this ordering, then it's very easy to answer about C. What will be the value of C? What will be the value of C? It will be equal to 4. Why? 2 plus 2 into 1. Does that make sense? Similarly, you will be able to calculate D, so on and so forth. So if you know the ordering, if you are able to decide about the ordering, then bottom-up logic is also very easy to implement. Why? Because inside the bottom-up logic, we start from the smallest sub-problem possible and use the order to build up larger problems. Does that make sense to everyone? Say yes or no. Is this making some sense? Guys, drop a yes or no in the chat section. Are you guys able to understand the concepts? What is memoization? How things goes, right? Okay. So let's just try to write that friend party problem. Let's just try to write that friend party problem in this bottom up manner. We have done one code in top down. Let's just try to have one code in bottom up. Okay. So let's say we have int friend party, right? We'll just pass the value n. Now we will build a vector int dp of size what? N, and let's say all the values are initially 0. This will be n plus 1. Here also we have n plus 1. Or we just need n. Let's see. For 4 friends. Yeah, 4 friends we can have just n. Right? We have only n unique states, right? Does that make sense? There is no concept for 0 friend. Okay. But just to make the calculations easy and have one based indexing, I can take n plus 1. Just to make the calculations easy and have one based indexing. Okay. Sure. Now, what will be the value of dp of 1? When you have only one friend, there is only one way. One friend, one way. What is the value of dp at 2? 2. 2 friends, 2 ways. Now, you will start your loop starting from I is equals to 3, going till what? N minus 1. Oh, sorry, going till what? N. Right? And every time, if you are not able to understand this loop, I have already made a template, which is I comma B is I is equals to A, I less than equal to B, I plus plus. Now, every time dp at I will be depending on what? dp at I minus 1 plus I minus 1 into dp at I minus 2. And we can return dp at n. Does that make sense? Does that make sense, guys? Because the ith friend, the number of ways in which I friends can go, just depends on what? dp at I minus 1 and I minus 1 into dp at I minus 2. And we can build the answer, right? So this time, let's just call the friend party problem. You don't need this dp array, right? And let's just try. So let's say for 3, we want the answer. Let's just try to calculate. Right? 4 ways are coming. Let's say we have 4 friends. Ten ways are coming. You can calculate. This will be 10. Does that make sense to everyone? Everybody, just say yes or no. Guys, are you able to understand this? Okay, okay, cool. Uh, okay, so let's just explain line number 65. So what I'm trying to say is that this is nothing. dp of 0 is nothing. dp of 1 is 1. Why? Because for I is equals to 1, you mean only one friend. So number of ways are what? 1. For I equals to 2, it is equals to 2. Why? Because two friends, either both of them can go alone or they can make a pair. Now, for any value I, let's say for I equal to 3, can I say dp at I will be equal to dp at I minus 1? This is I minus 1 plus I minus 1 into dp at I minus 2. Put the value of I equals to 3. So dp at 3 is equals to what? dp at 2 plus 2 into dp at 1. Are you able to understand this? Ayush, is this point clear? Then for every value of I from 3 to n, we can do the same thing. Does that make sense? Does that make sense? Okay, so let me just give you a problem. So this problem is coming from the CSES problem set. So all those people who don't know about CSES problem set, it's like a set of some starting problems that you guys can start with, right? Uh, and we'll try to submit a problem here. Okay. Okay. Are you able to see the problem, guys? Are you able to see the problem? Finger yes or no? If you are able to see the problem, read the problem, take 2 minutes and try to solve the problem. Write down your approaches in the chat section, right? And then we will try to solve the problem. I'm just coming in 2 minutes, right? Till then, try to think about the problem and write down your approaches in the chat section. Okay, so how many of you guys are able to understand this problem? Say a yes or no in the chat section. We can start then. How many of you guys are able to understand this? Drop a yes or no. This is a very, very easy problem. This is a very, very easy problem. I'm just increasing the level one by one, right? Okay, shall we start the discussion? Okay, cool. So the problem says that your task is to count the number of ways to construct some n by throwing a dice one or more times. Each throw produces an outcome between 1 and 6. Okay. So let's say that for n equal to 3, for n equal to 3, the dice can give you what? Either a 1 or a 1 again or a 1 again. So this can be one possible throw, or you can have 2 then a 1, or you can have 1 and a 2, or you can have directly a 3. So there are total 4 ways to throw a dice to get a n equal to 3. Yes or no? How many of you guys are able to understand the test case? Okay, cool. Now, in any DP problem, what I told you, you have to take the element of choice, try to build the recurrence, and then done. Take the element of choice, try to build the recurrence, and done. Right? Okay, so. So, let's say that for any value n, f of n defines number of ways you get n by throwing a dice multiple times. Can I define a function like this? Drop a yes or no? Yeah. Also, one more thing, count states. Count states. This is mainly required when you want to apply DP with a space constraint, right? Okay. Chalo. Now, how I can calculate this f of n? How I can calculate this f of n? Anyone? Guys, say yes or no. Are you able to understand this? Can I say that it will be equal to the number of ways in which you can get n minus 1? Why? Because let's say you want to make a 7. The number of ways in which you can make a 6, I can just throw a dice with a value 1 and I will get one possible state. Plus f of n minus 2. If you want to make a 7, the number of ways in which you can make a 5, I will throw what? I can throw either 2 ones or I can throw a 2. Does that make sense? Does that make sense? Right? So on and so forth. Can I build something like this? Can I build something like this, guys? Okay. So before writing the final recurrence, let's just visualize. Okay. Right. Cool. So let's say that in how many ways you can get a 1 on a dice? In how many ways you can get a 1? In how many ways you can get a 1? One way? Okay. In how many ways you can get a 0? One way, by getting nothing. There will be one way that will be null, similar to what? A null subset or an empty subset kind of a thing. Right? So there is one equivalent way. Can I say that? Right? Okay. How many ways you can get a 2? You can get a 2 by throwing a dice with a value 2, or the number of ways in which I can get a 1 plus I will throw a 1 again. Does that make sense? Does that make sense, guys? So how many ways to get a 2? 2 ways. How many ways to get a 3? Either you can throw a direct dice, that is, just get a direct value 3, or the number of ways in which you can throw a 2 then append a 1 after it. Does that make sense? Right? Or the number of ways in which you can throw a 1 and then append a 2 after it. And to get this 2, you can get this particular 2 in 2 more ways. That is, either directly give a 2 or give a 1 plus 1. So this will lead to what? 1 plus 2 or 1 plus 1 plus 1. Make sense to everyone? Guys, say yes or no. Are you able to get it? So any value I, f of I or f of n is equal to what? For all j belongs to 1 to 6, for all j belongs to 1 to 6, and this will be equal to plus equal to kind of f of I minus j if I minus j is greater than equal to 0. Does that make sense? So this will be equivalent to what? For f of 3, it is what? F of 3 minus 1 plus f of 3 minus 2 plus f of 3 minus 3. Does that make sense? So f of 3 minus 1 is what? 3 minus 1 is 2. F of 3 minus 2 is what? 1. F of 3 minus 3 is what? This is the throw when we will get direct a 3. This is equal to what? We get a 4. Are you guys able to understand it? Guys, say yes or no. Are you able to understand the logic? How I am building the recurrence relation. So every state in the worst case will depend on the previous 6 states. It will depend on the previous 6 states. Does that make sense? Shall I repeat it or shall we start the coding part? Guys, are you able to get an intuition on the recurrence? Anyone having any doubt? Okay, so let's just start the coding part. Maybe then we will be able to visualize it better. Okay, so how the cases are like, you will just get a value of n. N can be 10 raised to 6. Okay. So let's just make a new file. Command S. This is what, dice combination or what? Yeah. My favorite template. Okay. Int n, c in n. We'll write a function. Right. Let's just write it here only. Vector of int dp. What should be the size of my vector? Anyone? Can you see here? Can you see here? To calculate the value till 3, we needed what? 1, 2, 3, 4. 4 length array. To calculate a value of n, can I say n plus 1? Why? Because there will be n plus 1 unique states only. Right? Yeah. Let's just initialize everything with a 0. Then dp of 0 is equals to dp of 1 equals to 1. Right? Okay. Then we'll start from I is equals to 2 and go till n. We'll start from I is equals to 2 and I less than equal to n. Then we'll start a loop of j from 1 and go till 6 because the dice can have 6 faces. If at any point of time j is greater than I, can I break it? Can I break the loop? Let's say I was equal to 2, j becomes equal to 4 or j becomes equal to 3. So for j equal to 3, 4, 5, 6, we won't be able to calculate anything, right? Does that make sense? So we'll break it. Otherwise, we'll do dp at I is equals to dp at I plus dp at I minus j. Does that make sense? right? And here you can see that the answers can be really very big. So we need to have the answer modulo 10 raised per 9 plus 7. I already have a mod value 10 raised per 9 plus 7. So what I can do, mod, can I do this? And let's have a mod at last as well. And at the very last, I will just do C out dp at n, right? Let's just take a value 3, print it. It's coming as 4. Make sense? Right? Let's just try to submit it. Copy. Submit. Okay, so let me browse the file. Unacademy free live classes. Dice combination. Submit. Okay, testing ready. Accepted. Seems fine, everyone. Does this seems fine? Okay. So just for a note. Okay, so Kaustuv, I'll explain the modulo part. Just for a note. So I'll be solving the whole CSES problem set of dynamic programming in upcoming special free live classes next week. So next week I have 2 classes that will be free for all. You guys can join, and I'll be solving the whole CSCS dynamic programming problem set. So you guys can join and we will together solve the whole problem set. Okay, let me explain the modulo part. So generally in programming, what happens, the answers can be very large. So we need to constrain them under a certain boundary, right? That's why we take remainder values. So what happens if you have a value a plus b and you want to take a modulo c? So this is equivalent to saying a mod c plus b mod c whole mod c. Does that make sense? This is the part that I have done there, right? So you can learn about modular arithmetic more, right? You can get some logs, or I guess there are some videos as well available on the CodeChef's YouTube platform. You can just check them out. Guys, is this problem clear? Drop a yes or no. Shall we move to the next problem? Shall we move to the next problem, guys? Okay, cool. So the next problem is this is from the educational DP contest. This is the problem A. In the further videos, I might be solving the whole contest, maybe. Right. So the problem says that there are n stones numbered from 1 to n. There's a frog, starts from stone 1. He will repeat the following action some number of time to reach stone n. If the frog is at currently stone I, he can jump to stone I plus 1 or stone I plus 2. And here is a cost associated, which is hi minus hj, where h of I denotes the height at a particular stone. We need to calculate the minimum possible cost to reach the final stone n. Right, so let's say it is 10, 30, 40, 20. So let's say the values are 10, 30, 40, 20. So the final answer is 30. How? You can go to 10 to 30, then go from 30 to 20. So 10 to 30 will give a value 10 minus 30, plus 30 to 20 will give you 30 minus 20. This will be 20 plus 10, 30. Does that make sense? Sarju is asking, is memoization good approach? Okay. So till the time you guys think. So what happens in the case of bottom up is we compute all unique states, right? Every time we have to at least compute all the unique states. But sometimes in top down, we can calculate lesser number of states than the unique number of unique states and then also get the answer, right? So sometimes top down can even, I would say, act a bit faster, right? Generally, the space requirement is similar in both of them, right? Although there are some differences, you can optimize a lot in space in bottom up, right? I will discuss in further classes about that. So if you are like in an interview, you can like go for the memoization approach because the time is very less. But in competitive, try to have bottom up. No, Weber, there will be something more than that. There will be a bit more than that. Shall we start, guys? Shall we start the discussion? This is a very fairly easy problem. Okay. Let's define a function n which denotes the min cost to reach nth stone. Right? Okay. Now, let's just go one by one. What is the element of choice? What is the element of choice? From any stone x, or we can say that to any stone x, I might be coming from the stone x minus 2, or I might be coming from the stone x minus 1. This is the only element of choice available. Does that make sense? If I want to reach x, I have to come either from x minus 1 or x minus 2. This is the only choice available. Cool? Okay. Then try to find the recurrence. Okay. So let's say that I want to reach the nth stone. I want to reach the nth stone. What are the two stones that I might come from to reach to the nth stone? What are the last two stones? What are the possible choices for the last two stones that I should visit just before visiting the stone n? You guys tell me. That should be, I might be coming from n minus 1 or I might be coming from n minus 2. Does that make sense? You can just take a jump of 1 or you can take a jump of 2. So if you want to reach to nth stone, you have to at any point of time either come to the n minus 1th stone or n minus 2th stone. Does that make sense? Guys, say yes or no. So if you know the minimum cost to reach the n minus 1th stone, you know the minimum cost to reach the n minus 2th stone. If you know the minimum cost to reach the n minus 2th stone from some stone 1, right? And you know the minimum cost to reach the n minus 1th stone from some stone 1, then what will be the cost to reach from n minus 2 to n or n minus 1 to n? It will be equal to cost till f of n minus 1 plus mod of a of n minus a of n minus 1. This will be plus mod of a of n minus a of n minus 2. And we will take minimum from both. Does that make sense? Do you think this is going to be the recurrence relation? I can come from n minus 1th stone. So let us have the minimum cost already computed, anyhow, any cost, right? I can come from n minus 2th stone as well. Let's have the minimum cost already computed by dp. If I know these two costs, can I calculate the cost to reach n? Yes. If I'm coming from n minus 2, then my cost is what? Cost to reach n minus 2 plus a of n minus a of n minus 2 come out. If I know the cost to reach n minus 1, so to reach from n minus 1 to n, it will be f of n minus 1 plus a of n minus a of n minus 1. Does that make sense? Okay, so Amit says repeat. Amit, shall I repeat again? Or is this understood? Shall I repeat it again? Just brief. Okay. So the problem was that you have n stones, right? You have n stones. You start from the first stone. You have to reach the nth stone. You have a constraint. You can make a choice to the plus 1th stone or the plus 2th stone. That is, from here you can either go here or here. You can just take a 2 jump or a 1 jump. The cost associated with each jump is equals to a of j minus a of I if you are jumping from I to j. I to j, and this is the modulus value, right? Okay. You have to calculate the minimum cost to reach the nth stone. Okay. Now, what I want to try, I want to have a DP solution. So what is the element of choice here? What is the element of choice here? To reach the nth stone, you have to either come from the n minus 2th stone or you have to come from the n minus 1th stone. Can I say that? Can I say that? Right. So this is the element of choice. Now, let's say we define a function f. If it takes a parameter n, it determines us the minimum cost to reach the nth stone. Okay. So if anyhow, any cost, you know the minimum cost to reach the n minus 1th stone. So what will be the cost to reach from n minus 1 to the nth stone? It will be a of n minus a of n minus 1. So the minimum cost to reach from 1 to f of n while coming from f of n minus 1 will be f of n minus 1 plus this cost. Similarly, if you know the cost to reach to the n minus 2th stone in minimum cost, then from n minus 2, what will be the cost to f of n? It will be f of n minus 2 plus a of n minus a of n minus 2. This is the recurrence. Does that make sense? Does the recurrence make sense to you? Now, how many unique states are there? Or how many unique subproblems are there? N, you can start from 1, can go to 2, 3, so on and so forth till n, right? So there will be unique states will be n because minimum cost to reach the first stone, second stone. There is no 0th stone or there are no n plus 1 to greater stones, right? So there are n states. So we can have a dp of size n, and each state, here you can see that each state is determined by only one parameter. Each state is determined by one parameter. So 1D dp will suffice. Does that make sense? Guys, shall I write the code? Shall I write the code? Okay. So let us start. This is new file frog.cpp. Right, my basic template is coming. Okay. Cool. Now first we will take n, c in n. We'll make a vector int, name it as ARR, and size should be equal to n. Does that make sense to everyone? We'll make an array and we will just input the values. So loop from I 0 to n minus 1, c in ARR enter. Till now everything clear? Right? Okay. Now, what will be the value of dp at, okay, so let's just first define a dp. Vector of int dp, n states. Let's just initialize every state with a value 0. Right? Okay. Now, what should be done here? Anyone? What do you guys think should be the first step? We should define the base case. Okay. dp of 0, or let's say we make it n plus 1 so that we can have 1 based indexing. Right. dp of 1. What will be the value of dp of 1? What is the minimum cost to reach the first stone? It is equals to 0 only. Right, because you are already there. What will be the cost to reach the second stone? What will be the minimum cost to reach the second stone? You can just take a jump from the first to second stone, right? So it will be equal to what? Absolute value of ARR at 0 minus ARR at 1 minus ARR at 0. Right? We know these two values. Now we should start iterating from 3 and go till n. Right? This should be the iteration, and in every iteration we will just apply the recurrence. So dp at I is equals to minimum of. So we have the value of dp at I minus 1 plus absolute of ARR at I minus ARR at I minus 1. Right? Comma dp at I minus 2 plus absolute of ARR at I minus ARR at I minus 2. Does that make sense? Final value will be equal to what? dp at n. So let's just put the sample input 10, 30, 40, 20. Let's just try to run it. Okay, sorry. There might be some mistake. Just a second. Let's just take the array also one based, right? Because we can get some issues in that case. Right now, if the array is also one based, so we can have ARR at 2 minus ARR at 1, and now this will be fine. Does that make sense? We have made array also one index based to make the calculations easy. And now this will work pretty fine. Guys, is this point clear? Say yes or no. Try to submit it. You guys try to submit it on AdCoder, right? There is one small concept left. So when to apply DP? When to apply DP? Ashutosh, there can be more optimization because we can definitely optimize on space, right? Guys, for both the solutions, we can optimize over space. We can even solve it in O of 1 space and in O of n time. The problem name is frog. Problem name is frog, right? So this is space optimization that can be done in bottom-up solution. I'm not discussing it today. We are a bit less on time. I want to discuss this concept first, that when to apply DP, right? Okay. So there are two conditions. Everybody might have heard about them. That is overlapping subproblem and optimal substructure. If your problem is showing these two conditions, then you should definitely try to apply DP. Now, what is overlapping subproblem? We have already discussed that if there is any subproblem that is coming again and again, and its computation is going again and again, it's common, right? You are again and again computing. That's overlapping subproblem. Can anyone in the chat define what is optimal substructure in as easy manner as you can? What is optimal substructure? You guys define what is an optimal substructure. So guys, this question is very frequently asked. You will be asked this question n number of times, right? Okay, so Sogata says we have to calculate optimal path for every step. No, that is not the accurate definition for optimal substructure, I would say. That is a definition for optimal answer, I would say. What's an optimal answer, right? Okay, let's see. Each subtask to optimize. Somewhere close, Ranveer. For the final answer to be the optimal subproblem, the subproblem have to be computed optimally. Ashutosh is correct. Okay. So let's say that we have a larger problem and we need to find the optimal answer for this larger problem, right? So what we did, we divided it into multiple smaller subproblems, right? Okay. Now, if your solution is such that to calculate the optimal answer for the larger problem, it calculates the optimal answer for the smaller problems, and the contribution of all these smaller subproblems to generate the optimal answer of the larger problem is also optimal. That is, the answers from this optimal subproblems, optimal answers of these subproblems are contributing optimally to construct the answer for the larger subproblem. Then your problem is showing optimal substructure. This is why when you apply greedy algorithms, they also follow optimal substructure. Why? Because you took a smaller problem and at that point of time you took a greedy step. But that greedy step calculated the smaller subproblem optimally, and this smaller subproblem is contributing to the larger subproblem also optimally. So that's why greedy problem also have optimal substructure. But if you have overlapping subproblem along with greedy, along with optimal substructure, then DP is the way to go. Does that make sense? Yes. So to get the optimal solution for the bigger problem, your smaller subproblem should also be solved optimally, and they should contribute to construct the answer of the larger problem optimally, right? So let's say that for this frog problem only, if you wanted to calculate f of n, that is the minimum value for this f of n, and you have the minimum value of f of n minus 1, you have the minimum value of f of n minus 2, then by adding a of n minus a of n minus 1 and a of n minus a of n minus 2, these two smaller subproblems were calculated optimally, and now this recurrence is helping these two smaller subproblems to calculate the larger problem also optimally, and this is the optimal substructure. Does that make sense to everyone? Does that make sense to everyone? Right. Okay. So guys, generally when you have problems like counting something or calculating maximum value or calculating minimum value, and you have these two properties associated with it, and you are able to solve it recursively, you can go for the DP solution. Does that make sense? Right. Okay, cool. So there are like, for basic DP, for basic 1D, 2D DP, I can say there are like 7 to 8 variations. I'm saying for 1D, 2D DP, right? There are like 7 to 8 variations like subset problem, longest increasing subsequence problem, LCS problem, knapsack problem, so on and so forth. There are 8, 9 odd variations that will help you to solve all the basic problems very, very easily. Very, very easily. And all those variations we are going to discuss in the next live class that we will be having for the CSES problem set that I'm going to solve. It is having like 15, 16 odd problems. It will cover most of them, right? We'll be having more such classes. Don't worry for that. But do you guys understood all the concepts that we started with? I started with this very basic thing of adding one, and we ended up with something like the problem frog. I know this is beginner for a lot of people, but do you guys think this is understandable for a beginner level, or you are able to learn something new? Sure, Kaustubh, I am planning to take one. I'll be starting with recursion. Then I might take one on backtracking maybe. In backtracking, we will definitely, if I'll take the class, we'll try to visualize the whole call stack, every step in the call stack. I won't say that go and visualize that this answer is coming. In the recursion and backtracking session, I'll give you the visualization of the call stack of each step. That will help you a lot. So Agatha, the recursion session is on this Saturday. The CSES dynamic programming problem set session is next week. You can check the Unacademy website for getting the link, right? So if you guys liked today's session, if you guys understood that all the concepts, so you can subscribe to the Unacademy's competitive programming track, right? We have like a lot of instructors from ICPC, IOI medalists. People are working in Google, LinkedIn, Flipkart, Amazon, right? So people are from top tech giants. People have good understanding and a very good ratings on competitive programming platforms. So you guys can subscribe to the Unacademy's platform, right? And if you want some initial discount, so you can get a 10% discount by using the code Sanket 10, right? And we have a inaugural offer for October that if you will subscribe for a 1 month subscription, you can get it for 999. It's just a 1 month subscription, and this will be for all the courses for 1 month. If you opt for a 6 month or a 1 year subscription, you can get a 10% off using this code, right? But what I want to understand from you guys is that are you able to get a good step in DP? What is mutual exclusion? What is mutual exhaustiveness? So on and so forth. Are these concepts now relevant for you guys? Sweetie, I would say most of them would be understandable. If you're able to get the gist of 2D DP, then you will be able to solve all of them. Okay, so the Google form is not opening. Guys, don't worry. As soon as the session will end, the Google form will be open. And guys, do comment your doubts. If you still have any doubts, do comment your doubts in the comment section. I will definitely reply each and every doubt, whatever you guys will be having, right? And give us your suggestions. What more sessions you want, on what more topics you want suggestions. These sessions on YouTube and Unacademy special classes. We will definitely arrange more such sessions for you guys. Does that make sense? Drop your comments, drop your suggestions. We will definitely take a look at them, right? If you want to have some basic problems to practice, if you want some basic problems to practice, then you can go to CodeChef, right? And you can write CodeChef tags, right? And you can search for the tags of dynamic programming. So Agatha, in the CACS problem set, I will start with the 2DDP problems as well. Don't worry. Do attend that. Do attend that. That will be really beneficial for beginners, right? You can write dynamic programming and search for problems having the tags with dynamic programming, right? And you can sort by the accuracy and number of submissions and start solving any problem, right? And this will give you a better understanding on how tougher level problem goes with. Okay. Cool. Guys, drop your comments in the comment section, in the live comment section or the later comment section. Don't worry. We will definitely take a look on your suggestions. Any suggestions if you want to give, we can definitely inculcate that in the further sessions, right? So do join me on the next session of recursion that I'll be taking on Saturday. That will give you a good understanding on how recursion goes. And there are 2 sessions on Saturday, basic recursion 1 and basic recursion 2. Then I'm having one more session, I guess, on recursion problem solving, right? That is also there, I guess, on Monday somewhere. You can check the schedule. You can check the schedule on an Academy page. So we won't be discussing just basic recursion. We will be having a dedicated class on problem solving with recursion. So you will be able to visualize a lot of recurrence relation or direct recursive problems. And we will be solving a lot on competitive programming platforms like CodeChef and Spodge, right? So do check them out. And it was like really awesome experience to have a discussion with you guys on dynamic programming. I hope that everyone was able to learn something new. And if you have any doubts, do ask me. So Gada, as I said, I'll be taking the problems of 2DDP from the CACS problem set and give you the intuition on how you can think, right? Guys, in dynamic programming, try that you are not just mugging up the recurrence relation. Try to find the why this recurrence relation came, right? If someone was thinking it for the very first time, what would have been the thought? And not in dynamic programming, for any kind of problem, like let's say for heap sort, let's just take an example of heap sort. If someone wants to learn heap sort, don't just go read a blog, watch a video and learn heap sort. No, try to think after reading that, what would have been the intuition in someone's mind when someone would have thought of heap sort for the very first time. So what you can think that, let's say you already have selection sort in your mind, that what selection sort do for any ith index, it traverses the whole array at the right of I and extracts the minimum value. But this is what a linear search in selection sort, how you can optimize it. You want a minimum value, but you don't want to do a linear search. Maybe you can do binary search, but for that you need a sorted array, right? So how you can optimize? You can use an extra space of maybe heap to get the minimum value in O1 time, right? And remove that minimum value and reshuffle your heap in log n time. So in n log n, you can do something. So this can give you a basic idea on how to think on new algorithms. And these kind of things will definitely help you in paradigms like dynamic programming and divide and conquer, where most of the problems are new. So you should be able to get an intuition on how to think. Don't just solve the problem. It won't help. So 20 odd problems, if you just go solve, read the solution and submit it, it won't help you a lot. 10 good quality problems and you are able to understand the intuition that if this is the thing written, then why it is exactly written. Do some dry runs, right? Do some dry runs and think what would have been your approach if you would have been thinking for it for the very first time. Or maybe if you have to explain it to someone, how you can explain it to someone in as easy manner as possible. This will give you a basic understanding and a basic intuition on how to go forward with things. Does that make sense to everyone? Are you able to understand what I'm trying to say? Is this selection sort, heap sort logic relevant for you guys? So Ayush, the recurrence that I came with in party problem was that you want to arrange some permutations for n friends, right? Okay. Now, if I can anyhow calculate how the nth friend can go. So if we have fixed the fact that nth friend is going to go alone, then rest of the people are going to make some arrangements. They will give some count. If nth friend makes a pair, then rest of the n minus 2 people will make some arrangements and give a count. This is the basic intuition from where I can start the recurrence. Now there is a basic part that you can make multiple pairs, right? D can make a pair with A, D can make a pair with B, D can make a pair with C. So these will also contribute to the recurrence. And this is how I came up with the recurrence for the very first time. Does that make sense? Yeah, Ashutosh, if you like solve the CACS set and the AdCoder set, it will be a good head start for you, I would say. Right? You can solve some problems from Spoj and CodeChef as well. Like DP is like solve as many as problem as you can, and the better you will get again. Right? Okay. So let's just wrap up, guys. Let's just wrap up it. You guys were an awesome audience, and it was really awesome experience to have a discussion with you guys on introduction to dynamic programming. We discussed really good concepts today, and I hope you guys liked the lecture. Whatever your feedback is, drop your feedback in the comment section, and we will meet in the next session. So thank you guys. Good night. Take care. Stay healthy and keep coding. Bye-bye.